Hello guys, today we'll be reviewing topic D.3 in the IB Physics HR syllabus, which is motion in electromagnetic fields. So, here I'm assuming you've taken, of course, specifically you've taken D.2, which is electric and magnetic fields. So D.3 will dive in how uh, charges interact with a magnetic field and how they interact with the electric field and how basically magnetic and electric fields are very related. They're actually very related. In some points they are actually the exact same thing, but we'll not get into that. We'll get into how magnetic forces in general act on charged particles. So there are two things or two properties something has to have to in order to interact with a magnetic field. Number one, it must have charge. That means in order to interact with a magnetic field, you will also interact with an electric field since you have charge. Okay? The second thing is the more important, that in order for a particle to interact with a magnetic field, the particle must be moving. Okay? So, this law is derived showing that the magnetic force is directly proportional to the speed and charge of the particle. It is given by the force, let's call it Fm, equals QVB sine theta. So Q is charge, of course. So the greater the charge in coulombs, V is speed. So the greater the speed, the greater the magnetic force. And the new variable here is B, which is the magnetic field strength, given in a new unit called Tesla, derived by large T. And sine theta is the angle at which it interacts with the field. If it's parallel, the angle would be 90, so magnetic field strength would be maximum. Or sorry, if it's perpendicular, magnetic force would be maximum. If it is parallel, it would be 0. So this law shows how a particle of charge q and velocity v interact has a magnetic force m applied on it. Okay, but this is only for free charges, so we're assuming a literal one charge is flowing or going into a magnetic field. So like this one, let's say these are plates that have a magnetic field going from, let's say, this side, and this is a particle, let's say an electron, so has minus charge and going at, let's say, 3 times 10 to the 6 meters per second, and the magnetic field strength, let's say, is 100 Tesla, or it's much smaller actually. Let's say it's 1 milli Tesla. So if we wanted the force, well, F equals 1.6 times 10 to the negative 19, which is the charge of an electron, multiplied by the velocity, which is 3 times 10 to the 6, multiplied by magnetic field strength, which is 1 times 10 to the negative 3, since it's in milli Tesla. So using your calculator, 1.6 times 10 to the 19, 3 times 10 to the 6, multiplied by 1 times 10 to the negative, and this would give you the magnetic force equals 4.8 times 10 to the negative 16 newtons also. There is also another force that describes the movement of current in magnetic field. Well, current is simply the flow of electrons, or the flow of charge actually, but it's mostly electrons. So if you had a wire and that carried current in a magnetic field, the force on that wire would be given by the following equation: F equals B I, where B stays the same as the magnetic field strength, and also sine theta. I is the current in the wire, so the rate of flow of charge, and L is the length of the current within the magnetic field. So length of wire within field. So these are the two equations that describe the movement of charge and magnetic force. Okay, let's move on to the more important equation here, which is the interaction between two wires. So I'm gonna draw them down. Let's assume from the previous sections you would know that wires, assuming these are two wires, that wires that flow, that have current in the same direction, attract. So this would go there and this would go here. They attract each other. Okay? So there's an equation that describes the force per unit length of the wire in terms of their currents. It is given by the following equation. So the lengths of the wire, of course, have to be equal in order for this to work. If current is in opposite direction, they will repel. In the same direction, they will attract, so get closer to each other. So the force per unit length of two wires on each other equals mu node I1, the current in the first wire, multiplied by I2, the current in the second wire, divided by 2 pi multiplied by the distance between the two wires. This one is R. Mu node is known as the it's in your little booklet, but I often get confused. But mu node is known as the permeability of free space, and its value is 4 pi times 10 to the negative 7, and it would be newtons per ampere squared. And these are the currents, and this is the force. But a question that often comes up in exams is if wire A, say this is wire A, applies a force of 10 newtons on wire B, and the current in wire A is, for example, double that of wire B, they give you values, and the distance is kaza, is something. What is the force that wire B applies on wire A? So a student who isn't focused will just use the values given and plug it in into the equation, try to solve for F, but that is incorrect. Why? Well, Newton's law actually applies here, Newton's third law. When object A, which is this, the wire A, applies a force on wire B applies an opposite and equal force on wire A. So the force applied by one wire on the other is the same as the force applied from the other wire on that one. So this is a common question that comes up in exams, and they're testing your understanding of magnetic or fields in general, forces in general, and the application of Newton's law here is the same. So this actually section is done. So I think to get to know this section more, you need to solve a lot. So that's what I'm gonna do in this video. I'll solve questions on this. Okay, let's start with a but this has something to do. Okay, in a laboratory experiment, a charged particle moves in a circular path of radius 0.02 meters. In a magnetic field strength of B equals 0.5 Tesla. The speed of a particle V equals 1 times 10 to the 6. Write down the equation for the charge to mass ratio. So here is one of the questions that also comes up a lot In this case, a charged particle enters a magnetic field and moves in a circular path. So what does that mean? Well, since as it entered the magnetic field, it started going into a circular path, this means that the magnetic field, the magnetic force is the centripetal force. So to derive an equation for charge to mass, we have to equate the equation for force, which is QVB, to mv squared over r. So let's derive it. Since we know Fc here equals Fm, we can write it mv squared divided by r equals qvb. And since v cancels with the square, we got mv over r equals qb. And it is simply v over rb equals q over m. And that is the equation for charge to mass ratio. Okay. Now it's telling you to calculate. So you're given the charge to mass, you're given V, which is 1 times 10 to the 6. So we're just plugging in the values, divided by the radius, which is 0.02, multiplied by the strength, field strength, which is 0.5, equals 1 times 10 to the 6. I know it will equal 1 times 10 to the 7, but just let's make sure on the calculator. And that is correct, 1 times 10 to the 7. And do not forget your units here, it is coulombs per kilogram. Okay. C. Well, this question is not, I don't think it's in the curriculum, but it explains the significance of this ratio and identifying particles. So each particle actually, each isotope of particle has a different charge to mass ratio. Why is that? Well, isotopes, which you will know about later in topic E, but the same particle but different amount of neutrons. So the mass changes, but the charge doesn't changes. So the charge to mass ratio allows us to identify each particle and each isotope of a particle. So you could say in this question, it helps scientists identify elements and specific isotopes of elements. Okay, two long straight parallel wires separated by 0.08 meters, which is there also are. Currents I1 equals 10 and I2 equals 6. Derive the expression for force per unit length. Well, that's just the equation in your data booklet, which is force per unit length, equals the permeability of free space, the constant in your data booklet, I1 multiplied by I2 over 2 pi r. So calculate the force per unit length. Well, you're just gonna plug it in. So the force per unit length will equal, with this we know it's 4 pi times 10 to the negative 7 multiplied by 10 multiplied by 6 divided by 2 pi times 0.08, which will equal, say, 4 pi multiplied by 10 multiplied by 6 multiplied by 10 to the negative 7. Which will equal 1.5 times 10 to the negative 4. And do not forget your units, newtons per meter. Explain whether the force between the wires is attractive or repulsive and justify your answer. Well, in the question it states that they're in opposite directions, so you're going to state the answer. They are repulsive because currents are moving in opposite directions. And that's your 2 points. Or you could also say add that opposite currents create opposite magnetic fields which repel, just to make sure you get the 2 points. Oh. Okay, in particle accelerators, Charged particles are subjected to magnetic fields to increase their speed. A particle with mass 9.1 times 10 to the negative 31 kilograms. So just to let you know, that particle is actually an electron, which has the exact same mass that is stated, and a charge of 1.6 times 10 to the negative 19. You could have just said an electron to make it harder and wouldn't give you the mass, and you'd have to get them for the data booklet, but in this question he's making it easy for you. It enters a magnetic field of 1 Tesla, so B equals 1. With an initial velocity perpendicular, so perpendicular the force is maximum, so sine theta equals 1. So calculate the cyclotron frequency of the particle. Oh, sorry, this is actually not on us, the first part, but the second part is. Second part states determine the period of its circular motion. Okay, so then you hear circular motion, you equate the magnetic force to the you equate the magnetic force to the centripetal force, so mv squared divided by r equals qvb. Okay, let's cancel these, and I would like to isolate v, and I'll tell you why. So v here, if we send it, will be br over. So if you go back to topic 8.2, the final equation, you'll find that v, and here's actually asking you at the periodic time, so you have to go back to circular motion, and v equals 2 pi r divided by t. So we're gonna substitute that here. So 2 pi r over t, which is a periodic time, equals br divided by m. So the r's cancel out, and you just want t here, so we're gonna flip the fraction around, so it's gonna be t divided by 2 pi equals m divided by b, and since you only want the periodic time, it will be equal to 2 pi m over b. And oh, okay, sorry, so I made a mistake. It is brq here. You also have charge, then it will be brq here, that will be bq, and here it will also be q. So let's calculate, we're given everything, so it will be 2 pi stays the same, multiplied by the mass times 10 to the negative 31, divided by the charge only, since the magnetic field strength is 1. And it would be equal approximately 3.6 times 10 to the negative 11 seconds. There must be something wrong. Yes, the answer here is actually wrong. So, but here it is correct. Let's go on to another question. Okay, in a research facility, a particle with charge 1.5 times 10 to the negative 19 coulomb is studied as it moves in a region where magnetic field strength of B equals 0.3 and an electric field of 1000 newtons per coulomb are present, oriented perpendicular to each other. Analyze the trajectory of the particle if its velocity is additionally parallel to the electric field. So parallel to the electric field, it means it's perpendicular to the magnetic field, since the electric field is perpendicular to the magnetic field, meaning the magnetic force on it is maximum. And let's see the answer here. And the electric force equals the magnetic force, so you equate them. And actually, this is the only part where, okay, this is a paper 1 question. A charge of mass m and charge q is traveling in a uniform magnetic field with speed v, such that the magnetic force is F. So F equals QV, F equals QVB. The magnetic force on the particle of mass 2m, charge q, and speed 2v traveling in the same direction is, so what, question mark, so Kf, let's say Kb, a constant, equals 2m, which has nothing to do with the field strength, but the q and 2v, so it simply becomes 2f. You know why? Because mass has nothing to do with the magnetic force in this situation, so it becomes 2qvb, and the force would only double. I'm trying to find questions that, so let's solve this final question. They're all similar actually, but I'll try to find even. Okay, a proton of kinetic energy 2 mega electron volts, so EK equals 2 times 10 to the 6 EV, enters a region of uniform magnetic field B of magnitude 0.25. Perpendicular to its velocity. After some time, the electric field is applied in the same direction as B. Which of the following describes the resulting motion of the proton once both fields are active? The proton undergoes circular motion at a larger radius. The proton undergoes helical motion. The proton continues straight with no deflection, and the proton spirals inward, losing kinetic energy. Well, actually, this question is not part of the new curriculum, so leave it. But it actually moves in a helical path. A beam of electron travels in a region with perpendicular electric and magnetic fields. The electric field is 200 volts per meter, so 200, and the magnetic field is 0.5 times 10 to the negative 3 Tesla. What is the speed of electrons if they move undeflected? Well, here you assume that E equals the electric field strength equals the magnetic field strength. Oh, so E equals F over Q, so becomes F over Q equals, let's see how we'll do it. So let's write E as F over Q, or 200, the electric field strength, multiplied by Q, the charge, equals the magnetic field strength, which is QVB, and B is 0.5 So basically, once the charges cancel out, so it doesn't matter. So 200 equals something, V times 0.5 times 10 to the negative 3. So you divide both sides by 0.200 divided by 0.5 times 10 to the negative 3 will equal the speed you want, which is 4 times 10 to the 5. And it is the right answer. A particle of charge q and mass m enters a uniform field at a perpendicular to the field. What is the time taken to complete one full circular orbit? So it's basically telling us to derive the equation for periodic time. So let's do that again. We equate Fc equals the magnetic force Fm. So mv squared over r equals qvb. Okay? So if you rearrange for V, we get V equals QRB divided by M, and V equals 2 pi R over T equals QRB over M. So this cancels out with this, and we want to flip the fraction, so T over 2 pi equals M over QB. And it simply becomes T equals 2 pi M over QB. And let's see if that's one of the answers. Yet it is the correct answer. Let's move on to another question. When a wire with an current I is placed in magnetic field strength of B, it experiences a magnetic force F. What is the direction of the force? In a direction determined by I only, in a direction determined by B only, in the plane containing I and D, at a theta equals 90. Which of the following quantities does not affect the magnetic force on a moving charged particle? Speed of particle. Well, let's just write down the equation and let's pick the odd one out. So F equals Q V B. So what affects them is charge, velocity, and magnetic field strength. So speed is wrong, magnitude of charge is wrong, mass of particle is correct, since the final answer would state magnetic field strength, which is also incorrect. So by process of elimination, that is the mass. Which combination of field direction and charge will result in a clockwise circular path when viewed from above? Okay, it's gonna be negative, and so let's use the left-hand rule. So for clockwise, you want the force, which is your thumb, to be moving to the right. So the first answer says positive and into the page, so into the page, and you want the charge, okay, is positive and moving to the left and into the page. Will that be incorrect? Yes. Positive out of the page will also be incorrect. Negative, it's gonna be negative and into the page. Which of the following particles will experience a magnetic force in a magnetic field? A stationary neutron? Well, that does not even satisfy one of the two properties, which it has to have charge and move. A moving proton, well, that is correct since it had charge and is moving. And to solve more paper one questions, let's see. An alpha particle. Okay, with charge 3.2 times 10 to the negative 90 and mass equals 6.6 times 10 to the negative 27, moves in a path of circular radius r equals 5 times 10 to the negative 2 in a magnetic field of 0.2. What is the particle's speed? Well, mv v squared over r equals qv b. So let's just rearrange for v. V equals rqb over m, which we plug in 5 times 10 to the negative 2 multiplied by 1.6 times 10 to the negative 19 multiplied by 0.2. Oh, it's actually 3.2 times 10 to the negative 19, sorry. Multiplied by 0.2, all divided by 5 times 10 to the negative, all divided, by the mass, which is 6.6 times 10 to the negative 27. The velocity here is approximately 4.8 times 10 to the 5 meters per second. And we got something wrong. And there's something wrong here. Let's see. What did I do wrong? Well, I did nothing wrong actually. So I'm gonna see what's wrong with the answer. Well, the answers given here are wrong, but it would be equal to approximately 4.84 times 10 to the negative 5, times 10 to the 5, meters per second. And I want to let you know about this, if you know about more on topic E, that an alpha particle is a helium nucleus, and since you're given the mass of a proton, electron, or neutron in the data booklet, you are required to note, of course, that it consists of 2 protons, 2 electrons, 2 neutrons, and you're also required to know uh, that its mass is consists of 4 protons, or 2 protons and 2 neutrons. We exclude the electrons, and so given these things, they can actually give you the question without telling you the mass nor the charge of an alpha particle, and ask you its velocity. But this you will get to know more about in topic E. So today we reviewed topic D.3, which is motion in electromagnetic fields. We reviewed the 3 equations. I explained them, we solved some questions, and I hope you understood everything in this video, and I hope you go right now and solve some questions about this topic. It's a pretty small topic, it's a pretty fun topic, but I see many students struggling with its applications in relations to other topics, specifically the circular motion part, and it also has applications to topic E, which I will be solving about when I explain to you topic E, and you'll get to know it better. Thank you.